Alright then, now we're going to start studying this space. So it's the set of linear transformations from V to W. Suppose V and W are G modules. Then so is HOM VW. What is the actual action? Well, here I do know what order it goes in, so this is why I got confused earlier. When you want the action, the inverse goes inside the composition. To check that it's actually an action, see what happens when you apply two group elements. Alright, let's see here. What does this do to this function? It sends it to G prime times this function applied to G prime inverse of V. Now what does this function do? It multiplies F times G inverse applied to whatever's the input. G prime inverse of V. The G primes go together. The products on the outside can go together. And the inverses go together in the reverse order. And voila, we get G prime G acting on F of V. And you can check that this is linear, although that's a bit more of a pain. G dot F of alpha V plus beta W is GF G inverse applied to alpha V plus beta W. Well, the inner group action on V is linear. The transformation itself is linear and preserves the group action. Oh, no, it doesn't. That's the one thing we have to be careful of. That we are not assuming that F is G invariant. That is the one assumption we're not allowed to make. And then G is linear. When acting on vectors in W. And what do we get? We finally see that we have alpha G dot F applied to V plus beta G dot F applied to W. So yes, this is linear. Yes, it's good to remind ourselves here that we are acting on all linear transformations. And why are we interested in that? Well, let's look at this space of the subspace corresponding to the trivial representation. So remember, in general, these are supposed to be those F's. So it's that G dot F equals F. What does that mean with respect to the particular action we have for every element in the group? Well, that means that G times F composed with G inverse equals F for all G and G. Notice that means that you're saying F of G inverse of V is equal to G inverse of f of v for all G and G and all V and V. Notice if I swap the roles of G and G inverse, because that part isn't really as important, I'm just saying that the linear transformation is G invariant. So the subspace of G invariant functions. So we see then, in order to compute the dimension of the space of G invariant functions, it's enough to compute the trace of this corresponding linear operator, where here we're looking at G as the linear operator from this space of linear transformations to itself. Under this action, G dot L is GL G inverse. So suppose that V has eigenvalues lambda 1 through lambda n. Remember the corresponding, oh wait, hold on, let me be careful. We're going to fix G. Then there's a corresponding linear transformation from V to V and from W to W, because we've got a representation. Let's assume V has dimension n, W has dimension m. I'll use psi of G. So given these two G modules, we get these two representations, we end up with these two matrices. Well then, phi of G has eigenvalues and eigenvectors. Lambda 1 through lambda n, possibly with repeats, and eigenvectors v1 through vn. And psi of G has eigenvalues mu1 through mu n, and eigenvectors w1 through wm. So let Lij be the linear transformation from V to W, defined on the basis by taking Vj and sending it to Wi. And for the other eigenvectors, they get sent to 0. So more accurately, it takes one of these eigenvectors, Vk, either sends it to Wi when k is j, or 0. This is, of course, a valid linear transformation from V to W. We can see what happens when we act on it by G. What are we going to get? We're going to get G times Lij, G inverse Vk. Well, just any V actually, but let's just go ahead and put Vj for right now. Remember from last time, we had discussed this, that phi of G inverse would have eigenvalues lambda 1 conjugate through lambda n conjugate. So here we have an eigenvalue lambda j conjugate Vj. Since that's a scalar, we can pull it out entirely. And then we have g times Lij applied to Vj. By definition, that's lambda j conjugate times g of Wi. And so Wi has eigenvalue mu I. So we see GLij sends Vk to this product times mu Wi, which is the same thing as what we get when we apply Lij directly to Vj. Now if you work with other vectors, Vk when k is not j, you just get g times 0, which is 0. So we see in fact that Lij is an eigenvector for Hom VW. So we get this eigenvector for Hom VW with eigenvalue lambda I bar mu j. Now this is just for fixed I and j. And so what is the trace of g? Well, it's the sum of the eigenvalues, and we see that for every I and j we have a different eigenvalue. Even more importantly, the dimension of this vector space is n times m, because it also could be viewed as the vector space of n times m matrices. And so this is the maximum number of eigenvalues you could have, and we have all of them. We could rewrite this sum by factoring it. And what do we get? We get the trace of the group action on V, at least the conjugate of it, well, times the trace of the group action on W. So that's the trace for an individual group element in its action on this vector space. But what is our overall formula for this dimension? It was this sum, average sum of traces, which we now know, if I replace these with the corresponding characters, looks like this, which is the definition of the inner product. So from this formula, we've now discovered what the inner product tells you. The inner product of, so given two representations or G modules, the inner product of their characters is always a non-negative integer. What that integer is telling you is the dimension of the G invariant homomorphisms between the corresponding G modules. So that remarkable fact explains a lot of the inner product formulas. Namely, take any representation and take its character. Now take an irreducible, so chi is a character for a representation. take the inner product with an irreducible character. What should you get? Well, it should be the dimension of the G invariant subspaces from the corresponding G module V underlying this representation to this irreducible G module. Well, what can those representations, homomorphisms, possibly look like? Well, let's think about it. I mean, V, by Maschke's theorem, has to decompose as a direct sum into irreducibles. So you can define the linear transformation on each piece separately. So in some sense, you can treat each piece separately, but, well, the only way you can define phi from Vj to Vi and phi is not 0 is if Vj is isomorphic to Vi. So in other words, the only homomorphism or non-trivial homomorphisms come from a certain subspace. It's the subspace F, or F is V is, well, okay. It's a little hard to explain. So I think I'll just point out it's probably not too hard to see that based on linear independence results, this should be true. You can decompose your linear transformation into what it's doing on each separate subspace because they're independent subspaces. So the whole point is all these pieces don't matter except the Vj part. And so you're really reduced to looking at the dimension of Vi to the Ai in here. And so this is the first part of Schur's lemma. The zero map tells you that on most of these components, you can't get anything but 0. So the only component that matters is the component involving that irreducible submodule. But on there, the only transformations have to be scalars of the identity transformation. And so it turns out that its dimension has to be Ai itself. Namely, for each, From Schur's lemma, we see that the dimension of G invariant functions from Vi to Vi is 1. And so by this direct sum decomposition, this thing decomposes to Ai copies of this. And so it turns out this inner product tells you the number of copies of the irreducible representation, xi, inside this representation. In particular, you do get that xi, xj, irreducible characters are going to be 1 when I is equal to j and 0 otherwise. They are orthogonal. You'll quickly notice the thing that we haven't proven yet is that they actually form a basis for the space of class functions, and we'll prove that next. You need that in order to actually be able to conclude that you have one irreducible character for every class, for every conjugacy class, and therefore that the number of irreducible representations is the number of conjugacy classes. But for now, we at least have this orthogonality relation and this famous fact that about characters in general.